All right, gang. The purpose of this video is to motivate this big picture idea that coins are really a useful model for many, many real world problems. Uh, so in particular, in this video, what we'd like to do is we would like to illustrate a hidden pattern, if you will, when solving a coin flipping problem. And one of the things that we'll realize or that you'll hopefully realize, albeit with some practice, is that coins are very good at showing us how to solve lots of problems. And what's very nice about this is oftentimes there is a very simple formula that we can either memorize or use a calculator to compute probabilities. Uh, the problem at hand is going to be one you should be familiar with. I take a fair coin, like maybe this quarter, and I flip it 5 times, and I ask, what is the probability I get precisely 3 heads? Uh, the way that you would normally solve this, if you want it to be somewhat efficient, uh, is you would say, okay, I know that the probability of any event is the sum of the probabilities of all the outcomes in the event. So what that means for us, and by the way, for those of you who are unfamiliar or afraid of this Greek symbol here, this is a Greek sigma. And I hope that you understand that this Greek sigma right here, all it means is it means to add. So we're going to add up a bunch of things. Now, the problem with solving something using this strategy is that we usually have to count. And counting can, on one hand, be simple, but oftentimes it can be quite tedious, particularly if we have to count large numbers. So if we think about this problem, if we were to write out everything that happens, we know, hopefully, that when we flip a coin 5 times, there are 32 outcomes. Why is that? Because each flip, there's 2 outcomes. If I have 5 flips, I have 2 times 2 times 2 times 2 times 2, which is 2 to the 5th power, which is 32 outcomes. And in order to solve this using basic counting methods, we need to know precisely how many favorable outcomes there are out of the 32. And if you write them down and count properly, you'll recognize that there are 10 favorable outcomes. So this is, in one hand, this is not a hard problem. It's one that you can solve quite quickly if you know what you're doing, and the probability of this would be 10 divided by 32. So maybe you already know that, and if you do, great, but the point of this video is not to solve this problem. It's to show you that this problem is a special case of all kinds of other very important problems. So what we're going to do, though, is we're going to start by counting sort of the favorable outcomes, and we're going to do it in a way that hopefully leads us to recognizing a useful pattern. So the probability of getting 3 heads is the sum of the probabilities of all the outcomes in that event. And so if I were to list all the ways that I can get exactly 3 heads, I have 10 of them. I can go heads, 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 tails, tails. I can go heads, heads, tails, etc. So there are 10 ways in which I can get exactly 3 heads out of 5 tosses. Now, what's interesting about this is, on one hand, some of you might look at this and say, oh my God, this is so confusing. But what you need to remember is each one of these is just a number. This is a number. This is a number. This is a number. Number, 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 number. So I'm just adding 10 numbers together. And what's even more interesting is that each one of these numbers is exactly the same number. So if we go back to the axioms of our probability and our rules for probability, what we'll recognize is the probability of getting a head, 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 tails, tails, tails you think about this as head on the first, head on the second, head on the third, tail on the fourth, tail on the fifth toss. And since the coin is fair, we have a probability of 1/2 for all of these. And of course, 1/2 times itself 5 times is 1/2 to the fifth. What we need to understand then is that each one of those outcomes on the previous page, each one of them can be written as 1/2 to the fifth power. So if we go back and we substitute this value in, we get 1/2 to the fifth power, and we have 10 copies of this. This is for the first outcome. This is the second outcome, the third, fourth, fifth, sixth. These are all 10 of the favorable outcomes. Now, what you might be thinking is okay, you already solved this thing on the very first page, O'Grady, and you told us the answer was 10/32. Why are you making this problem look scary by putting all these scary symbols here? And again, the reason we do this is not to make the problem worse. It's because we're looking for a pattern. And thanks to all the algebra I learned as a kid, I recognize that if I have the same thing added up 10 times, that I can rewrite that in a very simple way. I can take 1/2 to the fifth, and if I'm adding it to itself 10 times, another way of writing that is 10 times 1/2 to the fifth. So essentially what I did is I factored it out. So I'm writing 1/2 to the fifth times 10 in a compact form. Now, if I do the arithmetic, 1/2 to the fifth is 1/32, and you'll see I get the same answer as I did real quickly on the first or second slide of 10 to the power 32. Of course, that reduces to 5/16, and so we would say that the probability of getting exactly 3 heads in 5 tosses is 5/16. Okay, great. What does all this mean? Well, as I said earlier, there is a hidden pattern here. And if you stop and think about what this number 10 means, number 10 represents how many different ways I can get 3 heads out of 5 tosses. And if you think about these counting techniques that you could read about in Chapter 4, and maybe I'll make a video on them too for those of you who are unfamiliar. There's a very useful notation for counting things. And in this particular problem, the one we're using is we are using what's called a binomial coefficient. This thing right here looks like a fraction, but it isn't. It is mathematical notation for 5 choose 3. So the way that you might want to think about this is we have 5 flips, and we want to count the number of ways that 3 of them can be heads. And so if you list them out, as you would see in the book, or as I did on a previous slide, in a previous video, if you list them out, you will see that there are 10 ways that you can obtain 3 heads out of 5 tosses. Now, this compact notation of 5 choose 3 is a little bit loaded. You might need to recall what this means, or you can just go to a calculator and you can, for example, in a Google search bar, if you write 5 in English, choose 3, it's going to spit out the number 10. You should pause this video and go do that. Again, go to a Google search bar and write 5, choose 3, and it's going to spit out the number 10. So again, this notation that looks like a fraction, but it's not. Notice there's no fraction bar. This reads 5 choose 3, and there's a formula for it, and every calculator knows that formula, and it turns out in this case, the number is 10. Okay, so why do we care about this? Well, we care about this because if we go back to solving the problem and we think about the number 10 in terms of 5 choose 3, we can say the probability of the probability of exactly 3 heads is 5 choose 3 times 1/2 to the 5th. Now, why is this formula useful? Well, if you look at this formula, the way I've written it, all the important numbers in the problem are screaming at us. You see the number 5 right here. You see the number 5 here. You see the number 3 here. And of course, you see the number 1/2 here. And why are these important? Well, these are the numbers that are specific to this problem. I was flipping the coin 5 times. The coin was fair, which means the probability of heads or tails is 1/2. And I am counting heads. So you'll see I want to know when there are 3 heads. So 3 heads corresponds to 5 choose 3. Or excuse me, the 3 in this thing for 5 choose 3. So again, let me reiterate all the important numbers in this problem. The 5, the 3, and the 1/2 are in this formula. Now, the beauty of all this, not only are they in this formula in this particular problem, we can extend this idea to flipping a coin any number of times. So if I go back to the first couple slides and I wrote everything out, and instead of saying I'm flipping the coin 5 times, I said I was flipping the coin 26 times, well then, instead of writing the n here, I would write 26. And instead of writing an n here, I would write 26. Similarly, instead of asking about 3 heads, if I wanted to know the probability of 8 heads, I would put an 8 here where k is. So now I have a perfectly valid formula. Sometimes we call these things functions, not to scare you if your math fears are high. But this is a function that spits out probabilities. And so what's really happening here, if you want a way of learning this and memorizing it and understanding it, the n choose k counts the number of outcomes with exactly k heads, and then the 1/2 to the n is the probability of each outcome. All right. Now, what's the real point in all this? Well, the real point in all this is not that throughout life all the nerds are interested in studying coins. Ooh, that one went over my head. That's not the real point in all this. The real point in all this is that we're looking for patterns to solve other problems, not just coin flipping problems. So what we're going to do is now we're going to assume the coin is not fair. Because if the coin is not fair, this introduces us with ideas to solve problems like, imagine I'm an insurance salesperson and somebody wants to buy insurance from me. Well, I might say, okay, great, I'm going to sell insurance, and the person comes to me and I have to determine how much premium or whatever I'm going to charge them for the insurance. And a question I might ask to myself, I might say, self, is this person going to get in an accident or require insurance? Or is this person not? So instead of asking the question heads or tails, I might be asking the question, will they get in an accident, yes or no? Another example might be, imagine I am a pharmaceutical company and I am going to be making medicine. The number one question I would ask is, will the medicine cause side effects? Yes or no? Now, in those two scenarios, we don't expect that every person buying insurance has a 50% chance of using it. Just like we don't expect every medication to have a 50% chance of being effective or a 50% chance of causing side effects. Or if I am making dry erase markers, I don't assume that there's a 50% chance this marker lasts a week. So in the real world, we often encounter things that don't happen in fairness. And we want a method for analyzing and quantifying probabilities in these scenarios. So what we can do is we can model our coin to be unfair. We can say the probability of heads is not 1/2, but it's some number p. And what's important to note is that p has to be less than or equal to 1, and it has to be greater than or equal to 0. That's the only thing that makes sense. Of course, if it were 0 or 1, that would be boring. But we'll just assume p is some number between 0 and 1. And that means if the probability of heads is p, the probability of tails must be the complement of that, 1 minus p. So if p is 1/2, then 1 minus p equals 1/2. And so that's a fair coin. But if p were equal to, say, 3/4, then 1 minus p would not be 3/4, but it would be 1/4. So if tails is 1/2, if heads is 1/2, tails is 1/2. If heads is 3/4, then tails must be 1/4. If heads were 90%, then tails would be 10%. Okay, so what we want to do is we want to go back to that coin problem, and we want to assume the coin is not fair. So everywhere that we had a 1/2, we are going to replace it with a p. Everywhere that we had a tails, we were going to replace it with 1 minus p. So for example, the probability of getting heads, 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 tails, tails would be p times p times p, and then 1 minus p times 1 minus p. Of course, we use exponents because it's a little cleaner to write. And so the probability of going heads, 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 tails, tails would be this, p cubed times 1 minus p squared. Beautiful. Now, if we did the problem the same as we did before, only this time we are not assuming the coin is fair, then there are still 10 ways where we can get heads 3 times. And so the probability of exactly 3 heads is now 10, but I'm going to write it as, remember, 5 choose 3 is 10. So instead of writing 10 here, I'm going to write 5 choose 3. And then the number of heads are 3, and the number of tails are 2, because if I get 3 heads, I must have 2 tails. And so this sort of gives you an easy way to memorize this formula. This is the total number of ways that you get favorable outcomes. These are the number of favorable outcomes, and these are the number of unfavorable outcomes. So the formula generalizes in the case that we're flipping this coin n times instead of 5. It generalizes like this. And an observation that I would encourage you to make is that the number of outcomes times the probability of each outcome is the structure of this. That is the structure of this formula. Okay, great. So let's summarize sort of what we did. What we did is we started with a very specific problem, that is flip a coin 5 times, determine the probability of getting exactly 3 heads. And we found that answer. Now, of course, we didn't calculate it because that's not what's important here. What's important is the structure of the formula. And then right away, we recognize that this extends to a much general formula. And this is, actually a great example of why we study mathematics. Studying mathematics allows us to take one problem and then find the hidden patterns that allow us to solve infinitely more problems. Just by solving this problem here, and we weren't worried about getting the answer. What we were more worried about is we were more worried about determining a pattern. We were more worried about understanding why it works. That's what we're more interested in. And so once we figured out a pattern, we can now take this pattern and apply it to all new types of problems. And really, at the end of the day, that is why we study mathematics, because it allows us to take a simpler problem, analyze it to death, and then figure out how we can take this simple problem and modify it so that we can solve new problems in the future. And this formula right here is so useful. It has a name. You may have heard of it before. This guy is called the binomial distribution, and it's going to be something we use a bunch more throughout this term. As always, I hope this video helped. If it didn't, I'm sorry. However, I would tell you, please, please, please reach out and ask me questions. My #1 job for this class is to be your best resource in learning. So please reach out if you have any questions or concerns, and best of luck, and I'll see you soon. Peace.